Hello and welcome to How to Math with Dr. Ian Lundholm. In today's episode, least squares and best approximations. All right, so we've already introduced the idea of least squares in one of our previous activities where we were finding the closest solution in a plane to a vector that was not in that plane. So I don't think it was this past activity, but I think it was the one before that. So probably activity number 6, if you want to look that up. Anyways, you may notice that today is not, normal PowerPoint slides. That is because there are no PowerPoint slides for this section. And so, yeah, here we go. We're back in OneNote. So, least squares. The idea here is that, we're given a system of equations that doesn't have an exact solution. Somehow, the column space of, our system of equations does not match up with the end result that we'd like to do. So, let me go ahead and just write here that throughout the entire experience today, B is not going to be in the column space of A. We have a system where we're kind of given an abundance of information at the beginning, and therefore there's not one right answer. So in these systems, A tends to be taller than it is long, just so that you guys know. And X is some vector and B is some vector that's as tall as A is. But yeah, in this picture down here, we have the column space here. The column space is U. And that's just all of the different linear combinations of the columns of A. And the idea here is that, B, the vector B, is outside of the column space. And what we're trying to do is to project B down onto the column space so that we can get kind of the best answer, even when we don't have an exact solution. And you can, this is still kind of review from that activity. But you can remember that we set the column space orthogonal to this vector that goes from the vector B to the column space, this one. And since we set that dot product equal to 0, we have orthogonality. And this dot product here, and this, is equivalent to this system of equations called the normal equations. And for some reason, this picture is not loading. Great. Let me see what that says. Okay, that just says that I'm going to write over top of it that these are called the normal equations. Since, this vector is orthogonal to every vector. No, that's not what I want to say. This vector is orthogonal to every vector in the column space. Keep going. So this is just a summary of what they're calling the best approximation theorem, where this set of normal equations gives us the best approximation when we don't have an exact solution. It minimizes the length of this vector, which is the vector that goes from our column space to our vector B that we're hoping to land on. Yeah, it minimizes the length of that vector, and this is an optimal solution in some way. So another thing is that if the columns of A are linearly independent, so I'm looking at number 2 here, then A transpose A is invertible, and there's a unique solution for this optimal vector Z. This is, what we would call our best approximation. Do know that in this section there are a lot of familiar letters thrown around in ways that maybe aren't, I don't know, the way that you're used to seeing them. Here, Z is just the best vector that would fit here, the best approximation. So there's no exact solution here for X. Z is the best approximation. It's not a Z value, it's a vector. Yeah. So if the columns of A are linearly independent, we're able to get that optimal solution by doing this long matrix multiplication with the inverse of A transpose A times A transpose times B. This is often the case. It's often the case that the columns of A are linearly independent. Like I said before, A is normally tall and skinny, and therefore would have vectors with lots of components, but relatively few vectors. And so oftentimes these vectors are coming from some high dimensional space since they are long. Yeah, and often, if as long as there's nothing too much special about the way that they're created, I mean, yes, often those are linearly independent, and we do have one solution. If you're taking real life data and that the whole randomness of measuring things is part of it, you're almost certain to get linearly independent columns when you're actually working with real world data. Okay, so there's that. We've talked about that. Let's look at our first example here. This is example 5.6.1, and I do believe I made a GeoGebra for this. We have a system of linear equations, 3 equations and 2 unknowns. This is like an overdetermined system, where if we had 2 equations and 2 unknowns, then we'd be able to probably solve for a unique solution. And if they were the same line, then we would have an infinite number of solutions. I guess we could have no solutions if they were, parallel lines. But in this case, we've got 3 linear equations that are not all going to intersect at one spot. They're going to form a triangle. So I think I have a picture of this. Let me see if I can open. Here's the 2D line version. Don't say it's fine. And I'm gonna get rid of this real quick and that. So these are our 3 original equations in that problem. And you can see they don't have any one solution. In this context, it's a little bit weird. I even hesitated showing you this, but after we use the normal equations to solve for a best approximation of this system, this is the answer that we end up getting. This point, I named it K. But honestly, I am not 100% sure in this context kind of what geometrically we would be looking for in terms of creating that least squares solution, like what we are trying to optimize, what distances and stuff. Normally it's not as helpful to think about it this way. I did, you know, recreate the original three equations using the using the least squares best approximation, and it does show you how, you know, each of these lines gets shifted in a direction perpendicular to the line, so that they all intersect at this point K. But I think the more helpful visualization of this problem would be instead to view this as a matrix equation, where our matrix A looks like 3, 1, 2, negative 1, 2, 1. So I'm just looking, at the coefficients there, of x and y. And then our vector B over here would be 4, 0, 1. And looking at it in terms of this matrix equation, or even if you wanted to think about it in terms of like a vector equation, we're asking what linear combination of these two column vectors would land us on the vector B. And so the geometric interpretation that I think would be more helpful for us to look at and analyze would be this one. Don't save. Bye-bye. Here I've, already put these vectors in. U is the first column of that matrix A. V is the second column of that matrix A. And I created this blue plane based on the span of those two vectors. So this blue plane is the column space of A. Now, the vector W is actually the vector B in the problem as I just wrote it. So sorry about that. It's just, it's the vector that's outside of the plane. And so this matrix equation does not have a solution, but we can get a best approximation to what that would be. And in order to get there, we would multiply A transpose on the left hand side both times. So let's do this. 3, 1, 2, negative 1, 2, 1. 3, 1, 2, negative 1, 2, 1. There we go. 3, 1, 2, negative 1, 2, 1. And our vector B, 4, 0, 1. So actually doing that multiplication gives us, since this is a 2 by 3 matrix and this is a 3 by 2 matrix, the result that we get here is a 2 by 2 matrix when we do this multiplication. And we get 14, 1, 1, and 6. And I think we've mentioned this before, but notice that this matrix, A transpose A, is symmetric. And that will always be the case. A transpose A and also A transpose are symmetric matrices. So all the good stuff that we learned about the eigenvalues of symmetric matrices will apply here. So here we still got x and y, and then this is a 2 by 3 times a 3 by 1, so we're going to get a 2 by 1 vector as an answer here. This one is 14 and negative 3. And then solving this system, which has been, compressed from the original system in some sense. Now we can solve for values of x and y that, actually get us somewhere. So they would call our book would call this vector z as in terms of the best approximation, and z ends up being 1/83rd times 87, times 87, negative 56 as an answer. So that's what happens in GeoGebra here. The way that I got the vector A, and I have completely lost the left-hand side of the screen somehow. Lovely. Lovely. Come on, GeoGebra. Oh, the GeoGebra app. Let's get back here. I want to see this. Yay. Okay. And how I got this vector A was taking a linear combination of u and v, where that, 87/83rds was the coefficient on u, and negative 56/83 was the coefficient on v, or that's fine. And so A is the closest vector in the column space to the vector W. And so that's a best approximation solution. Okay, moving back to OneNote. There's our work. Looking good. Okay. Moving on to example 5.6.2. This one does not have a nice GeoGebra representation, mainly because we're starting to get into an amount of data that would be difficult to visualize, geometrically, and because we're three-dimensional beings. What we have here is some statistics. This problem reads, good grief. The average number G of goals per game scored by a hockey team or hockey player seems to be related linearly to two factors: the number x1 of years of experience and the number x2 of goals in the preceding 10 games. The data on the following page were collected on 4 players. Find a linear function that best fits these data. So to me, honestly, this linear function does look like a 3D plane. And maybe I could have visualized that part, but the important parts that would have been nice to visualize are the columns of this matrix A, which are going to be 4 units long. So, here we've got player 1, player 2, player 3, player 4. Each of them get their own rows. And in order to find this mystery linear function, the easiest way for me to think through this is to actually set up equations plugging in each of these numbers for each player. So if we were going to make an equation for player 1, that equation would look like 0.8 equals A0 plus A1 times X1, which is 5, plus A2 times X2, which is 3. I'll do player 2, and then I'm probably not going to do the other ones for the sake of time. But Player 2, yeah, you'd have 0 0.8 again, you'd have A0 again. It would be A1 times its X1 value, which is 3, times A2 times 4 is its X2 value. So you'd end up getting two more equations here for player 3 and player 4. And the idea is that you'd have another overdetermined system. This time the variables being A0, A1, and A2. You'd have those three variables in four equations. And as a matrix equation, again, you'd have a matrix that is, taller than it is wide. The matrix equation would look like 1, 5, 3, 1, 3, 4, 1, 1, 5, and 1, 2, 1, based on the data that we have here. Do notice that we get this column of ones. Why do we get that column of ones? Well, it's because A0 keeps popping up in every single one of these equations, and none of our data is getting multiplied times A0, and so that value just doesn't change. And that's fine. That happens a lot of times. That this A0 number is kind of like a starting point that we'll get to analyze when we look through the results of this one. But yeah, notice that, this is basically the X1 column, and this is the X2 column of that chart above. Here, the matrix would be A0, the vector would be A1, A0, A1, and A2. And our result vector would be, all of the G values. So 0.8, 0.8, horrible, 0.6, and 0.4. But yeah, we have another overdetermined system where we have fewer variables than we do equations. So, yeah. Again, in this context, what we could do is create the normal equations by multiplying through. Normal equations by multiplying by A transpose on the left. And then solve the system A transpose AX equals A transpose B. Doing row reduction, something like that, to get your best approximation solution. In this case, the best approximation solution, we'll call that, again, Z is taking the place of X here, but the best approximation solution would be 0.14, 0.09, and 0.08. So if we take this and look back up at the hockey data, we get, a function G equals 0.14, that's A0, plus 0.09 X1 plus 0.08 X2, 0.09 and 0.08. And what does this mean? This means that even if a player was coming in with 0 years of experience and 0 goals. So 0 years of experience. Oh gosh, I aimed that wrong. 0 years of experience, 0 goals. That our linear function would predict that even if a person was coming in with 0, they would still get, you know, they would, yeah, still earn 0.14 of a goal. That's an average, of course. That means that they'd score a goal every, I don't know, 8 games, 9 games, something like that. But the factors of, yeah, more years of experience, that adds on another 900ths average of a goal per year. And we add on another zero point 0.8 average of a goal for the number of goals in the preceding 10 games. So, yeah, you would use this function as a way to predict future performance. And, this is definitely useful to people who are in, fields where you want to predict the future, which is pretty much everything from finance to sports, to technology, all that kind of stuff. This is how you analyze data. This is a very, very small scale. You would probably get better models using larger amounts of data and probably considering, different functional relationships between the variables. And we're going to see that you can use linear algebra to find optimal solutions that are not just lines, that are not just linear functions. We're going to be able to, fit exponential curves. We're going to be able to fit trigonometric curves, whatever you want. Linear algebra has you covered whenever you're dealing with an overdetermined system like this. All right. So cool. That function gives us some predictive power, hopefully. Here we're going to talk about least squares approximation. And when somebody's, talking about least squares, what they mean is you've got this scatter plot of data. All of these, I'm going to recolor these. These pink dots are like the dots that you would have on a scatter plot beforehand. That's like the original data. And the task that we've been given is fit a trend line to this data that would, predict future performance, or maybe you're interpolating between data points. But yeah, find a line of best fit for this data that would describe what's going on. All of these distances are labeled with, d sub some number. We've got d1, di, and dn here. Those distances are the things that we are minimizing the sum of the squares. So we're minimizing sum of squares of distances. You will see that here. What? Okay, I didn't copy that down, so I'm going to write it. But yeah, you're trying to minimize, d1 squared plus di squared, and then eventually you get to dn when you have n points. But yeah, we use the squares of the distances because it fits really nicely mathematically with, all the stuff that we've been doing in terms of minimizing length, um, each one of these things is, shoot, one of these distances up above. Yeah, there's D1, this would be D2, this whole thing. That would be Dn. And what we're really doing is minimizing the length of this vector, a vector between the actual observed y values and the function's y values that we're trying to fit to this data. And this kind of a thing should look pretty familiar, because it's exactly the same kind of thing that we were trying to minimize earlier. We were trying to minimize the distance between, a vector outside the column space to the column space. Here, we're minimizing a vector outside the column space, y, to a vector in the column space, f of x. And so, we're doing the same thing. This least squares approximation is literally what we've been doing so far. We're going to continue to, make matrices like this. We've got the matrix M here. Again, since we're fitting a line in this context, you might think of it as like we're fitting a line y equals mx plus b. And, do know that I'm using y here in a different way than this vector y. You could say, now this would actually be better, less confusing to just say that this is f of x equals mx plus b, and where m is the slope and b is the y-intercept. But this matrix M is the matrix that you would get when you've got n points given to you on a scatter plot, and you want to fit a line to this data. And so we're minimizing the sum of the squares of the distances because it fits in really nicely with just dot products and distances, everything that we've talked about recently. I don't know that there's much to say. Do know that this thing is exactly what I was trying to communicate up here. We're trying to fit an approximating line, where Z0 is playing the role of B and Z1 is playing the role of M for the slope. Do know that in this book, they want you to, they are consistently using the smallest degree terms and setting those to the left, and then the higher degree terms go to the right. Know that when you go to input answers into your online homework, because I learned that the hard way. I've been creating and previewing your final exam, and there is a least squares problem on there. And just make sure that when you are, fitting your quadratic equation, that your quadratic equation, instead of the normal way where you think of it as like in standard form, ax squared plus bx plus c, you're going to want to start c first. So you want to start with the lowest degree term to the left and the highest degree term to the right. And that'll make your matrix match what they're expecting. Anyways, I think we should keep going with examples because that is kind of the best way to understand these, I think. Here, we're just given 5 different data points, and we're trying to fit a least squares approximating line here. So You can go and you could use this theorem as like a template for being able to solve this kind of a problem. If you are a person who likes to, like have a form and then plug things into the form. When I do these problems, I like to kind of work from more of a first principles perspective where I'm working with things that I am familiar with and then create the matrix equations based off of what makes sense to me. And so in this context, yeah, we would come up with 5 different linear equations. Yeah, well, it's fine. Where, y is playing it, yeah, is playing the role of f of x. Anyways, for the first point, we would have the equation 1 equals b plus m times 1 because that's our x value. And for the next one, we would have 2, that's our y value, equals b plus m times 3. That's our x value. And so on and so forth. Shoot. Messed that up. The y value is 3, the x value is 4. And yes, there's 2 more. I'll do it real quick. No. I wrote an equal sign in that problem. There we go. There we go. So here's our system of equations with 5 equations, 2 unknowns. Yeah. And what is this? Our book would like us to use the letters M and Y here for the matrix and the vector. Earlier on, we were calling these A, AX times, AX equals B. And there's even M's and B's and Y's down in here. So this lesson is an alphabet soup, but I hope that you're able to follow along and realize which ones of these are just numbers, which ones of these are vectors. I'm sorry that this gets hairy. Anyways, I'm using B and M here as the y-intercept and the slope of various lines. Let's make this matrix. I'm going to call it A, just so that we're clear on that. The matrix A here would look like a bunch of 1s initially. Those are all of our B's. There's 1B, the coefficient on B. And then the second column would be 1, 3, 4, 6, 7. Our vector X would be B and M. And then this is our vector B, but the resultant vector, 1, 2, 3, 4, 5. I did not even notice that the first time that I did this. It counts up. Anyways, again, you would solve this by creating the normal system of equations where you multiply both sides by a transpose. And let me see if I have this here. Yeah, the normal equations, when you get down to it, would look like A transpose A would be 2 by 2. It would be 5, 21, 21, and 111. X would be exactly the way that we left it. And A transpose times our resultant vector B here would be 15 and 78. And it's that 2x2 system of linear equations that we solve in order to get the best approximation solution. Now, I mean, again, our book would be using kind of the notation Z here for the actual best approximation solution. And it turns out that, the y-intercept turns out to be 0.66 after doing row reduction. Literally, you just put this into an augmented matrix and row reduce. And this one turns out to be 0.24. Let's take a look at what this would have been graphically. So we're going to go back to GeoGebra. Please, GeoGebra. You're killing me. 5.6.3. Don't save. We're back. Okay. So here we have those 5 points that were given us in the chart in the beginning. And it was our task to create the least squares, the line of best fit. And here I have actually input those values in. So this is the best fit line. But yeah, I mean, it could have been any line. We could switch. We could let M and B do their thing and change around if we wanted. But all of these lines would not be as good of a fit. Whoa, okay. Cool. So we found the slope and we found the y-intercept that gave us the best approximation. No big deal. Moving on. Here's one level up where instead of just fitting some linear equation, here we're fitting any polynomial that we want to. So this is a polynomial of degree m. And yeah, as long as you have more data points than the degree of your polynomial, you should be able to use least squares as long as those data points are, real life measurements and not just... You can't have a bunch of points that are just stacked on top of each other that all have the same x value and have different y values, because then you would get a line of best fit that is vertical and that has an undefined slope. But as long as you have some variability in your data and you're not just using all the same x value, you should be able to fit a polynomial to it. And again, this looks really, really similar. We end up getting another column of ones in the front, and then just based on how many degrees your polynomial is, the coefficients end up, coming here in your matrix. So that's it at a very high level. But again, I think the most productive thing would be to go ahead and look at an example of, for instance, let's try to fit a quadratic polynomial. This is something that will be very similar to our activity 8 on Friday. We will have a special guest appearance by, oh goodness, I'm blanking on his name now. Oh, Nathan Baker. He's going to, throw a bouncy ball up in the air for us, and we are going to create a quadratic function that models the trajectory of that bouncy ball, or yeah, models the position of that bouncy ball as it flies through the air. I would have done the same thing with you guys in class in real time if we were there, but we're gonna have to use last year's video in order to make this activities work. But yeah, this is exactly what we're gonna do on the activity. Anyways, let's get to it. We are given 5 points here, and we are trying to find the best quadratic function that fits this data. So I'm going to open GeoGebra again just so that we know what we're aiming for here. In this problem, we are given these 5 points of data, and you can see that, yeah, it looks like it's, kind of following an opening up parabola shape. This is the parabola that we end up finding through our work in this problem. And I feel like I've done this kind of problem with you guys before. It's been a while maybe. But yeah, again, to create a system of linear equations to solve for these 3 values, we want, I should use a different color. Yeah, we're going to be solving for z0, z1, and z2. Yeah, we just plug these points into our equation here and come up with a bunch of linear equations. So for our first point, the y value is 3. Z0 would just be Z0. Z1 is just Z1. The x value is -3. And let's put that in parentheses. And then Z2 times x squared. So we actually square, that -3 and get 9. And so on and so forth. We have our y value. Z0 stays there. Z1's there. The x value is -1. And the x value squared is 1. And so, yeah, we end up coming up with 5. Geez, that went far. We end up coming with 5 of these equations. We end up getting a matrix equation that has all of these in it. So here, I'll go ahead and just write that matrix equation. This portion will be a vector that we call y. 3, 1, 1, 2, 4. Those are all of the y values of the points. For our matrix A or M, whatever you want to call it, here we would have all the coefficients that we have. So Z0 first, a bunch of coefficients of 1 for Z0. For Z1, we would have a bunch of different coefficients. All of those would just be x values. So -3, -1, 0, 1, and 3. And then in the rightmost column, we would have the squares of all of those. So -3 squared is 9. We've got 1, 0, 1, and 9 again. And then that is multiplied times our z vector of Z0 through Z1 through Z2. Okay. So there's our matrix equation version of this one. And again, in order to solve it, we would multiply by M transpose on the left on both sides, then row reduce. The normal equations would be 3x3 system of equations. This would be M transpose M, 5, 0, 20, 0, 20, 0, 20, 0, 164. Again, that is a symmetric matrix. Oof. And M transpose Y would look like 11, 4, and 66. Yeah, and so solving that, doing augmented matrix, then row reduction, gets you the least squares solution that I kind of already showed you. The vector z looks like 1.15, 0.2, and 0.26. And those are our plays. Open this thing. Don't save. Yeah, those are the coefficients. I wrote them as A, B, and C here. But yeah, those are the coefficients on our quadratic interpolating polynomial. So that's pretty cool. What did I want to say? Oh yeah, and do remember back to that activity 6 that we did already, where I had you do this problem the first way, where you multiply by A transpose on both sides and then use row reduction to finish it out. I had you do it a second way, where instead of using just these plain old columns of M, I had you turn those columns of M into an orthogonal basis for the subspace. Make sure that you normalize them so that they had a length of 1. And then some really nice things happen, like M transpose M actually turns out to be the identity matrix. And you're able to solve the system just by multiplying M transpose times Y rather than having to do, the row reduction in the end. Normally, computationally, the row reduction, I think, ends up being faster just for a computer to do. But whenever you can, work with matrices that have, columns that are of unit length and are orthogonal to one another, that is very advantageous. It makes your life easier. So that's what we're going to be talking about here in the near future. About we talked about diagonalizing matrices. We're going to be talking about orthogonally diagonalizing matrices using the Gram-Schmidt procedure and all that kind of stuff. That's something that we're looking forward to. This is how you find a least squares approximating quadratic polynomial. Moving on. Sorry if I'm taking too long. Again, so this was basically level 2, finding a polynomial. Level 1 was finding a best fit for a linear equation. Level 3, and our final level for today, will be to take just any functions that you want to. Functions like trig functions, exponential functions, whatever functions you want. Based on the way that you see your data unfolding, maybe you think, oh, hey, a sigmoid function would work really well to model what's going on with this data. This is how you'd say fit a sigmoid function to a graph or a scatter plot. A bunch of data points. Here we've got n data points, and we've got m different functions. The normal equations work out again to give you an optimal solution in this case. So, as an example, if we're given 3 points and we want to find an approximating function that includes, yes, a linear term, but also an exponential term, we could do that. Again, we would be operating off of, this kind of an equation. And in order to set up our initial system of equations that we will eventually solve using the normal equations, we would, again, just plug the points in wherever we have our y values. The first y value is 0. Then we'd have r0, whatever, or z0, whatever. This is just our first weight. We'd plug in our x value here, -1. And then we'd have R1 times 2 to the x power. Our x is still -1. So that'll end up being 1/2. For the next one, we would have 1 for our y value and 0 for our x value. For the last one, we would have 4 for our y value and 1 for our x value. There. And so our matrix would look like -1, 1/2, 0, 1, 1, 2. We'd have R0 and R1 hanging out here. And then we'd have 0, 1, 4 hanging out there. And again, we could use the normal equations to get a best approximation solution for this system. Here's what it looks like on GeoGebra. Hopefully it's there. I know that I made one for it. We can do this real quick. Here, let's just start with a new one. Don't save. I made this already on GeoGebra. GeoGebra is the worst in terms of actually saving what you make. Ooh, this semester with GeoGebra has been a fight. Anyways, I want to create 3 points. And those points were -1, 0, 0, 1, and 1, 4. Oh, missed. Boom. And you can see that, yes, this does kind of look like it grows exponentially, and that's maybe a reason why 2 to the x was part of this, part of this whole thing. And in our case, we would end up finding out that R0 would be 10/11 and R1 would be 16/11. And so what I could do here, please, would be to type in R0 is 10/11, and that would be times x, and we would add that to 16/11, that's R1, times 2 to the x. Let's go ahead and throw times in there for, look, here we go, x, boom. And then we get this lovely, I don't want to create another point, good grief. Bam, get out of here, D. yeah, we get this lovely interpolating function that is part linear function and part exponential function. And yeah, feel free to Frankenstein different um, functions together based on how you feel like your data looks. This is the math that's going on behind the scenes whenever you use Excel to create lines of best fit. So I hope that this has been, I don't know, an interesting lesson. I think that this stuff is among the most applicable and powerful stuff that we talk about throughout the entire semester. Um, and I'm sorry not to be able to actually be with you in person to talk about this. And so I have to ramble alone here in my house. Anyways, I hope that you guys are enjoying your wonderful Wednesday. And if you have taken time to listen to the end of this video, thank you for continuing to participate in class. Um, I'll see you on Friday for an activity. It should be fun. All right. See you later. Bye.